In this problem, we're asked to calculate the limit as n goes to infinity of an for this sequence. Now this is a complicated sequence and it's going to require some algebraic trickery, but it's actually an important sequence and shows up a lot in math. And so we're going to work all the way through it and learn how we can work these problems out. Okay, so here's the idea. So we'd like to calculate the limit of an, which will be the limit as n goes to infinity of 1 plus 14 over n to the n. The issue is that if I plug in infinity in for n, I get something weird happening. I get 0 for 14 over infinity, so that's 1 plus 0 is 1, but then raised to the infinity. And infinity is weird when dealing with limits, and it doesn't always work exactly the way that you would like it to work. And so we have to take very great care in figuring out what happens. And we have to do a trick, a math trick. How do I get variables out of the exponent? Well, we get variables out of the exponent by taking natural logs. So what I'm actually going to do is I'm going to take the limit of, as n goes to infinity, of the natural log of an. We're going to calculate that limit and then use that to get the limit that we actually want in the end. Well, that's the limit as n goes to infinity of the natural log of 1 plus 14 over n to the n, which means that we can bring this n down. That's the power of natural logs. That's the limit as n goes to infinity of n times natural log of 1 plus 14 over n. At this point, what happens when I plug infinity in? If I plug infinity in here, I'm going to get infinity times the natural log of 1. But natural log of 1 is 0, so that's going to be infinity times 0. And we have to remember some of our limit tricks for dealing with something like infinity times 0. And if you remember, that is L'Hopital's rule. L'Hopital's rule works for 0 over 0, or infinity over infinity, or we can do some algebra to turn this into one of those two cases. So we're going to use L'Hopital's rule, but before we do that, we have to make this look like 0 over 0, or infinity over infinity. And we're going to do that as follows. We're going to do that by writing that as limit as n goes to infinity of natural log of 1 plus 14 over n. And then I'm going to put that n that I see here in the denominator. But think about going from here to here. It makes a lot more sense. If I go from here to here, then I'm going to multiply by n over 1. And multiplying by n over 1 would make this look exactly like this. So we haven't done anything. We've just done some regular algebra. But the power is that, but now when I plug infinity in, I get ln of 1, which is 0, and I get 1 over infinity, which is 0. So that has turned this into 0 over 0, and we can actually apply L'Hopital's rule. Remember that to apply L'Hopital's rule, we take the derivative of the top and the derivative of the bottom independently. It's not the quotient rule. We just take the derivative of the numerator and the derivative of the denominator. So that is the limit as n goes to infinity. If I take the derivative of the top, well, that's going to be 1 over 1 plus 14 over n, 1 over what's inside times the derivative of what's inside. And the derivative of what's inside is, well, that's, the 1 goes to 0, that's 14 n to the minus 1, so its derivative is negative 14 n to the minus 2, which is negative 14 over n squared. So that's the derivative of the numerator. The derivative of the denominator, well, that's n to the minus 1, so the derivative of that is negative n to the negative 2, which is negative 1 over n squared. At this point, we can bring the negative 1 over n squared back up by multiplying by the reciprocal. So that'll be now n squared over negative 1. Simplifying what we have, the n squareds will cancel, the negatives will cancel. And that leaves me with limit as n goes to infinity of 1 over 1 plus 14 over n times 14. Now what happens? When I plug n equal infinity in, this goes to 0, and I get 1 over 1 plus 0 times 14, which is 14. But we're not done. The limit is not 14. Remember that we stuck that natural log in there as a trick in order to get the n out of the exponent. So what we have actually discovered is that the limit as n goes to infinity of natural log of an is 14. That's where we are. All that work has gotten us that far. We have to go one more step to finish the problem. Because natural log is a continuous function, this is really the powerful step here. I can actually bring natural log outside of the limit. I'm not going to go through all of the details of that, but this is essentially the definition of continuous. A function is continuous if and only if the limit of the function is the same as the function of the limit. And so what that means is, this is what we want. We want the limit as an of an as n goes to infinity, which means I can solve for it by turning this log function, this log equation, into an exponential function. E to the 14 is what's inside. Limit as n goes to infinity of an is e to the 14. And that's what we wanted. You very well may be asked to reproduce something similar to this on a quiz or an exam. It is an important idea. This can be taken. You can take the limit as n goes to infinity of 1 plus 1 over n to the n. Well, this problem had a 14 in here, but if we didn't, that 14 became e to the 14. If this were 1, it would become e to the 1. This can be taken as the definition of e. This is a very important number in calculus. So this one is, in fact, e.